Well, earthquakes are one of the major natural hazards and disasters we know of. They can kill upwards of hundreds of thousands of people per event. Let's take the 2010 Haiti earthquake, upwards of 200,000 deaths. The Indonesia earthquake in the earlier part of 2000s, I think it was 2006, also upwards of 250,000 deaths. These are major events, but the problem with them is they happen very infrequently, so people tend to forget. It's not like you get a hurricane season every year to remind you of it. It happens every 50, 100, 200, even 400 years. And it's something, once it hits, it really devastates an entire region.
Dr. Ganoum has received an $800,000 grant to develop computer simulations that predict earthquake impacts on reinforced buildings.
The project we just got from the National Institute of Standards and Technology is really to develop the next generation of simulation tools for those older buildings, specifically for the columns themselves that are the biggest risk for the building. So once the columns go, usually the whole building goes. That project is delivering these tools in an open source format to all the engineers, and pretty much anywhere in the world. This will be available online for anybody to take it, whether they're in California or in Indonesia. These tools will allow the engineers to make better decisions on the buildings they have, the existing buildings that are of danger to collapse and kill people during earthquakes. And also these tools will allow them to better design the next generation of buildings to reduce the damage. This is a survey I did in 2010 in Haiti, in January. Right after their big earthquake, they lost 80% of their buildings in their downtown core, close to 200,000 deaths. I was there about a week after the earthquake with the United Nations, surveying, seeing what buildings are left standing that they could actually use. So their government was shut down because they didn't have buildings to go anywhere. And so just kind of showing you a little bit of what those pictures look like, what kind of damage we're expecting. This is a column damage. This is very standard, typical column damage, where you have this kind of shear failure at the base, a failure at the top. This is what we're worried about. Now, fortunately for this building, the earthquake did not push it far enough to bring it all the way down.
Okay.
So this is an intermediate state of damage. This is another building, another picture like that. This is the full row. I believe that was a school building, if I'm not mistaken, where it shows damage but not collapse. This is what we want that model to give us. So not just give us the forces and deformations of the building, but also tell the engineer, you have this type of damage at the end of it.
As Dr. Ganoum tells us, this new technology is needed not only around the world, but right here in the United States.
They're estimating as Southern California, also Northern California, San Francisco are due for a big one. So is Seattle and that area. They're due for an even much bigger one. It's a subduction zone, so the earthquakes there can reach magnitudes 9. Whereas in California, they may top off at magnitude 8 due to how the geology is working. So these big earthquakes are due. They can happen tomorrow, or we can be another 20 years without them. But it's inevitable, it will come.
Let's take a look at this next generation impact technology in action, focusing on a building column.
So here's a column that's being pushed back and forth. You can see it going here. This is the strains or the local deformations. So we can measure, we can see the cracks. You can see where the cracks are forming as it's being pushed back and forth. And you see how the damage progresses there. So now we're able to measure this in the lab. From this, we can actually quantify damage very precisely. In the past, we had to do it visually. Concrete fell off here or this, that. Here we have exactly what's going on. We have it very well quantified, so we can develop the next generation tools with it. The ultimate goal is where we're going with this is we really want engineers to have the tools to make those decisions, to save the lives, and to improve community resilience. If you look back in history, every time big earthquake hit, usually cities get devastated and they never really recover. So we want to go there. We want to have these tools be used by the engineers. And by giving the engineers those tools, I think the future will be the cities will be much more encouraged to actually mandate higher levels of performance of their buildings, and all this will bring us to a point where we have safer buildings, more cost-effective buildings, and communities that are able to ride out these big, massive disasters and keep going without having to shut down or lose their livelihood or even lose the city itself.